Okay, let's look at some of the final problems. I'm going to be going over a couple from the autumn 2019 final. The first one I suggest you look at. And let's look at 2a, one of the trickier ones. You're supposed to take the derivative of this. Since we have something with an x to the power of something with an x, we have to use logarithmic differentiation. So we rewrite this as e to the ln of the same thing, 1 plus x squared to the inverse power of x. The whole point of that is then we can take the power to the front of the ln, because the ln of something to a power is a power times the ln of the base. So that's the same as e to the ln. And this is why I should never use a pen. E to the power in the front, which is inverse tangent of x times the ln of the base. So that's why we do it this way, because we can put the power in front. Now we take the derivative, and the derivative of e to the anything is e to the anything, which is this, which is this. So y prime, you can always write the original function, 1 plus x squared, which is usually the best way to do it. It's cleanest. It's usually less writing. You don't have to write e to the ln's and everything. Then it's always times the derivative of the power, right? Derivative of e to the something is e to the something times the derivative of the something. It's always going to be a product rule, because you always have the power times the ln of the base. So we know it's going to be a plus in there, so that's why I put a parentheses right away. Okay, the derivative of inverse tangent, if you forget, you can look it up. It's 1 over 1 plus x squared times ln of 1 plus x squared plus the first one, inverse tangent of x, times the derivative of ln of 1 plus x squared. The derivative of ln of anything is 1 over that thing, 1 plus x squared times the derivative of the thing, the chain rule part. The derivative of 1 is 0, the derivative of x squared is 2x, so times 2x. And basically we're done. And you could just leave it like this. This is the derivative. To get their answer, they simplified it. They took, since they both have a 1 over 1 plus x squared, they took that out. So they got y prime equals 1 over 1 plus x squared times 1 plus x squared to the inverse tangent of x. And then inside the parentheses, they only have, here they only have a ln of 1 plus x squared plus, and here they have a 2x left and the tangent. So it's nice to put the 2x first. Inverse tangent of x, because they took out the 1 over 1 plus x squared. Now, the tricky part here is, this is the same thing as 1 plus x squared to the negative 1, right? 1 over something is the same as what's in the bottom of the negative 1. So, if we wrote that as 1 plus x squared to the negative 1, we have 1 plus x squared to the negative 1 times 1 plus x squared to the inverse tangent of x. And when we multiply bases to the power, we just add the powers. So this is the same thing as y prime equals 1 plus x squared to the inverse tangent of x minus 1. Because we have this one, we add them, and here it's negative, so it's minus 1 times everything here. And that's the way they wrote it, as 1 plus x squared to the inverse tangent minus 1 times this. This is a nice simplification. I doubt, or highly doubt, anybody taking the test actually did that last step, wrote that as minus 1. It's not obvious to see that. It's kind of tricky. But that's a nice clean way to write it. So, okay, now let's do, again, this part here is all you needed to do. Stop right there. That's good enough. Okay, let's do 2b. 2b was that they give you this function, they define this function to be x squared sine 1 over x squared when x is not equal to 0. And when it's equal to 0, they're just going to make it be 0, because we have sine of 1 over 0, which is 1 over infinity, which is not defined. But we want to have this function defined everywhere, so it's continuous. So they said, okay, we'll just make it 0 there. Now it's a perfectly well-behaved function. It's no holes or anything. It's defined everywhere. Because in one place it's weird, but it's going to make it 0. Okay. Then they say, okay, what's the slope at 0? What is the derivative when x equals 0? And they want you to use the definition of the derivative. So the definition of the derivative is the derivative of x is limit as h goes to 0, and you should remember this stuff or look it up, of f of x plus h minus f of x divided by h. And if you remember, this is the hard way to do it. We had to, everywhere there's an x, we had to plug in x plus h minus the function of x. It's really messy, a lot of algebra, and then we learned a lot of rules to avoid using this, right? Because it's a real pain. But they want to show that you know how to do this. And it's actually a really good way to solve this problem. So, fortunately, we don't need to do the complicated part, because plug in x plus h here, and we have x plus h squared and 1 over x plus h squared, and it'd be a nightmare, because we want it at 0. So f prime at 0 is the same thing, but everywhere there's an x, we plug in a 0, which is really nice. So here's an x, so that we plug in 0 for x, that just becomes f of h. Plug in 0 for x, that's f of 0 divided by h. Okay, well that's the limit as h goes to 0. F of h means wherever there's an x, you plug in h into the function. So that's h squared sine of 1 over h squared. F of 0 is 0. We just said when x equals 0, the function is 0. So that's minus 0 divided by h. Okay, the h's cancel. We can plug in h equals 0 now, except we have this thing here in the bottom, but we can figure that out. So this is the same thing as the limit as h goes to 0 of h sine 1 over h squared, because the squared cancels out this h there. Now the tricky part here then is saying, okay, sine, the biggest or smallest this can be is 1, right? It ranges from 1 all the way to negative 1. Sine of anything, I don't care if it's, whatever, as h goes to 0, can never be bigger than 1 or less than negative 1. As h goes to 0, though, 0 times 1 is 0, 0 times negative 1 is 0, and 0 times anything in between is 0. So this is equal to 0. And that's a perfectly good argument. That's like using the squeeze theorem, kind of. Well, is it? I'm not sure it is. But anyway, the point is, since this one is always between 1 and negative 1, if this one goes to 0, then this whole thing goes to 0. So the derivative of 0, the f prime of 0 is 0. And that's how we showed that. Okay, now let's do number 9. Number 9 is one of the linear approximations ones. All the tests seem to have one of those, so there will be one on your test. And what they say is they have this function 3y equals tangent negative 1 of y minus x. And they want to know at 0, 0, they want you to find a linear approximation to point 0, 0 of this function. Okay, now all they had to really tell us was x equals 0. If x equals 0, then what is y? And we could figure that out. If x equals 0 here, then the inverse tangent has to be equal, x equals 0, then 3y has to be the inverse tangent of y. Anyway, the only way that could have worked is if y equals 0. But they were nice, because that's kind of tricky. So they said, I don't want you to be worrying about that in the final. We'll just tell you when x equals 0, y is 0. But again, I'm just saying a lot of times they don't tell you that what y is. You have to figure it out. When x equals 0, what is y? Okay, so here's our point, and we always need a point and a slope. So what we need to find is our slope, which of course is the derivative of y. We can't solve for y here and take the derivative, so we have to do it implicitly. So the derivative of 3y, so right, we're taking d dx of the whole thing. The derivative of 3y is just 3y prime. Remember, if it was y squared, it'd be 6y times y prime, but a y by itself is just y prime. That's the easiest one there is. The derivative inverse tangent of anything is 1 over that thing, 1 over 1 minus that thing squared. So y minus x squared. It's plus. Derivative inverse tangent is 1 over 1 plus x squared, like we did in the earlier problem. Times the derivative of what's inside. The derivative of y is y prime. The derivative of x, because we're taking respect to x, is 1, so y prime minus 1. Okay, now we want this at 0, 0. We want y prime when x equals 0 and y equals 0. Well, that makes it real easy, because this whole thing then is just equal to 1. Because if y is 0 when x equals 0, y equals 0, 0 squared is 0, so it's just 1 over 1, which is 1. So all we have left is 3y prime equals y prime minus 1. So right after you take the derivative, it's okay to plug in the point, because we want the derivative, the slope, when x equals 0. In this case, y is 0 when x equals 0. So you can always figure it out. Again, they told us that, but if you didn't know that, figure out when x equals 0, what is y, because as soon as you take the derivative, you can plug in the numbers and it makes your algebra a lot easier, like it does here. This is much easier. Now we just solve for y prime. So plug the y prime over here. 2y prime equals negative 1, or y prime is negative 1/2. So the slope is negative 1/2. So now we do the y minus y1 equals mx minus x1. Easiest case, y1 is 0, x1 is 0. So we just have y equals the slope times x. The slope is negative 1/2. So this is our linear approximation. Y is negative 1/2 x. So then they said, okay, what if x is 0.004, what is y? So that's super easy. Y is negative 1/2 of 0.004, which is negative 0.002. And we're done. So all the linear approximations are just like we did in class. You have a point, and you got to find a slope, which is y prime. And your job is to figure out the derivative of y prime is. Here we had to do implicit differentiation. Sometimes you don't. But you always find out that's y prime at that point, right? Which makes it easier. Like right here, we could plug in at the point 0. They're both 0 there. But that's always how you do them. And then you find the equation, the linear approximation. We make it into a line by using this formula with a point and a slope. So it's just algebra 1 stuff after that. And then you can plug in the point they give you, the x they give you, to find out an approximation for the y. That's why they often wrote you should use squiggly lines here. So y is about negative 0.002 because this is an approximation. We're approximating a curve with a straight line, which works pretty well if you're close to the point. 0.0004 is close to 0, close to x equals 0. So this is probably a really good approximation. Okay, hope that helps.